Hello everyone, this is Tanjim. Now I will be presenting my project for ECE 591, securing digital designs with logic locking using deep learning. I have splitted the project into two segments. One is background and motivation, and the other one is the project itself. That means project insights. Basically, the problem starts from the semiconductor supply chain. The use of pre-verified hardware intellectual property in system-on-chip designs has become a prevalent practice in the semiconductor industry. However, the global economic trend that dictates a horizontal business model incorporates many untrusted parties in the modern chip design flow. In particular, most chip designers rely on potentially untrusted third-party fabrication facilities. Such a trend diminishes a chip designer's control on the IPs and makes them vulnerable to various forms of attacks, including piracy, reverse engineering, overproduction, and malicious modifications. For example, I have stated here some challenges for reverse engineering on hardware designs. To address these security issues, hardware obfuscation or logic locking techniques have been actively studied for the past decade. So, what is logic locking? In short, logic locking is a schema to lock a design in such a way that the design will generate faulty outputs if wrong key inputs are provided. You can think logic locking as a lock on the door. If correct key is inserted, then it will be opened. There are two main types of logic locking: functional and structural. In functional logic locking, certain key bits are added on a specific function. As for example, I have added a key on an adder. The adder will work if correct key bit is provided. It can be thought as a key inserted on a black box. But the functional logic locking creates a door for key gates detection and key bits extraction, as it cannot be able to hide designed content. This is why structural logic locking comes into play. In structural logic locking, key bits are inserted on inside the design contents. Whereas, look at this example. Here, a XNOR gate is inserted inside a design as it is a XNOR design as it is a XNOR gate. So the key bit will be 1, but it will be thrice easy to guess for an attacker to guess by seeing an XNOR gate. For this, logic simplification is needed. Logic simplification is also known as logic synthesis. So, what does the logic synthesis do? Basically, it transforms a structural design into a new one so that the attacker are confused to guess. Here the inserted XNOR gate is look like a XOR gate, which is confusing, but the key bit is remaining the same. But still, there are some problems of structural logic locking. That is, they are local and predictable in nature. Now we will see these observations. Basically, three types of structural transformations can be happened, and I mark all of them as three levels. Level 1 is when there is no changes on after synthesis of a design. Level 2 will be happened when key gates will remain intact but the surrounding gates will be transformed. Both of these is very easy to guess as there is no change in the key gates, right? Level 3 is much more complex, and that will be occurred when key gates will mix with the surrounding gates and transformed into a new structure. Look at this table. Level 1 and level 2 are responsible for 95% of the logic transformation, which is basically node transformation on key gates, and pretty easy for an attacker to attack on a design and predict the keys. The observations are taken from seven largest benchmarks from ISCAS 85, and locking is done here randomly, which is mostly the popular method of logic locking. Moreover, statistical analysis shows that only 50 rules are responsible for 30% of transformations, and thousands rules are responsible for 81% transformation. These statistics is also gathered from the same seven largest benchmarks. So this is very much predictable, and the vulnerabilities pave the way for generating machine learning model to learn from these. So far I have discussed about the random XOR or XNOR based logic locking. There are also several types of logic locking. For example, random marks based secure logic locking, cyclic obfuscations. But none of them are automated. In every logic locking schema stated here needs human intervention. There is also some logic locking attacks to break the designs, as for example, Sail, Omla, Snapshot are the attacks that is based on machine learning models, and SAT KSA is traditional heuristics based attacks. The goal of every attack is to predict the correct key bits. For this project, I have implemented only SAT attack. Let's dive into the project. The main challenge of this project is to prepare a dataset. The dataset is created automatically from the designs. At first, designs are locked with random XOR or XNOR based logic locking. As a design is a connected of gates and wires, so the gates can be treated as nodes and wires can be treated as edges. So in this way, the design is firstly converted into internal graphs. Now, random logic locking schema will be applied into the graph so that the main output of the design does not change. An example is shown here from ISCAS 85 benchmark, how the key bits and key gates are inserted on a graph. This is the overall flowchart of dataset generation. After locking the netlist or designs, set attack is applied here to guess key bits, and then a comparison is measured on the predicted key bits by set versus the known key bits which I have inserted in the design. I labeled this comparison as loss metric, so the lower the loss, the better the locking will be. There are three control points for the loss metric. If the loss is less or equal than the threshold loss, then it will generate the features from the key gates and dump it into numpy array. If the loss is greater than the threshold value, it will relock again the netlist in those places where the SAT attack predicts correctly. And lastly, if the loss cannot ever reach into the threshold, then it will be terminated after a certain amount of iterations and dump the feature as numpy array. Now, at this moment, what we will see what is inside the numpy arrays. The X demonstrates a flattened array of certain size. Basically, the size will be dependent on number of locality gates and the number of unique gates in the designs. So for locality 3 gates and 9 unique gate types in the design, the number array will be 1 by 36. The first 9 is for the connectivity between gates and the first 9 is for the connectivity between gates, that is represented by adjacency matrix, and the rest of the for each of the gate types. The surrounding gates are found by breadth first search algorithm. Gate types are hot encoded and connectivity is shown as adjacency matrix. Similarly, y.numpy array has two values 0 or 1. 0 is for the correct SAT predicted key and 1 is for wrong SAT prediction. The training and testing dataset is gathered in the same way, but training data contains only features from the key gates and corresponding levels, where test data contains features from all gates to dictate proper location to be logged. The training data is collected from various benchmark designs from ECE's 85 hardware IPs, except for the target benchmark, which will be needed to log automatically by deep learning model. 80% of data is used for training and 20% is used for the validation. Number of epochs is decided based on the minimum validation loss so that the model does not overfit. Here is the sample model architecture for the data shape of 1 by 36. The input is split into 4 channels and fed it into different dense layers. And lastly, all of them are concatenated and fed into sigmoid dense layer. This is the sample code for the previous model. Lastly, the most important part is the result. Here I plotted every SAT iteration and corresponding loss based on random logic logging, which starts from 39% loss. It fluctuates because it is random in nature. The red point is the achievement of this project. It shows 24% loss on its first iteration when the logic locking is done automatically. Remember, not randomly. Now, there can be several improvements as there are a lot of points that is not covered so far in the project till now. As for example, more dataset can be applied pre-processing of data, joint attacks, that is as for example I have only applied SAT attack, which is traditional. So SAT and ML based attacks also can be applied here jointly. There can be different training mechanisms, different network architectures, proper proper threshold measuring also, and also post processing. That's all my presentation. Thank you for your patience.